Okay, so now let's look at an actual types of decay that things might go through. So you have different isotopes. Remember, the neutrons in an atom make things stable or unstable a lot of times, as well as the size does. So some are never very stable. But anyway, that isotope can then cause that decay. And there's three different types: alpha decay, beta decay, and gamma decay. And I have this pretty thing shown here, but a lot of times they look a little uglier. Alpha, a lot of times, looks like a fish. Beta is usually just a slanted and a long-tailed bee. And gamma doesn't always look as much like a Y as it does kind of a squiggly. That might be a little too much, but you get the general idea. Just keep an eye out for those. Those are just the symbols we use to represent alpha, beta, and gamma decay. First up here, we have alpha decay. So alpha decay shoots off a alpha particle, which really is just a helium nucleus. It's 2 protons and 2 neutrons, which is the nuclei of a helium atom. It's going to have a +2 charge because neutrons have no charge, protons have +2. It's the largest and slowest, stopped by a sheet of paper. However, it is going to change your parent nucleus into a daughter nucleus by decreasing the mass by 4 and the atomic number by 2, which makes sense because you're getting rid of 2 protons and 2 neutrons. This also is an important type of decay because it's how we learn so much about other atoms. In fact, we realize that most atoms are filled with empty space because they were shooting alpha particles at a gold sheet and seeing how many of them actually bounced back and how many went straight through. The majority went straight through, even though it's a nice positively charged thing and would hit a nucleus. It's how we learned a lot of different things. You can look up the Goldfull experiment if you wish to know more. This is how that would look in a nice, neat little equation. You're going to have to be able to do this. So we're starting with a parent element or parent nuclei. This is uranium, and it has a mass, that's what goes up top, and a atomic number, that's what defines it as uranium. It's number of protons. So under alpha decay, we're going to get rid of a helium nucleus, which is an alpha particle, has a mass of 4 and 2 protons. Well, really, you're subtracting that from the parent, so you're going to get whatever element is then 90 protons, because you have to get rid of 2 of your protons from your parent one. And so your daughter nuclei is just whatever is 2 protons lower than your parent one if you're doing an alpha decay. In this case, it is TH for thorium, which is just element number 90. So notice you take your parent, subtract the helium protons 2, you get your new element. That fills out that part. The next is you're not taking the mass from the periodic table. You have to take the mass of your parent nuclei or atom, which would be uranium here, and you're subtracting the 4 from the alpha particle, and so you get 234 for thorium. That might not be its normal mass, which also may make it an isotope, which may make it unstable. But the important thing is it has to balance those numbers. Next up, we have beta decay, and in beta decay, you get a beta particle. What's that? Oh, it's just an electron. That's all beta decay is. It's a single electron leaving from it. Now, that's not all that's happening in beta decay. In beta decay, we're actually dealing with quantum particles beyond subatomic particles, known as the quarks, which are being rearranged. And so you're actually taking a neutron, because still it has to do with that isotope, and it's breaking down enough to release an electron, but also convert into a proton, because they're very similar. It's just the quarks that make them up. In fact, it's something crazy like 2 up and a down make a neutron, and 2 down and an up make a proton. But that doesn't really make any sense to your level, or really mine, to be honest, and a lot of it's theoretical, so it's hard to figure out. But we do know that this happens during beta decay, so that we do get a neutron turning into a proton, but releasing an electron from the nuclei as well. So it's all made up of the same stuff. So it's smaller and faster. It's basically electricity is what it is. And so you can stop that with a certain amount of shielding. Even aluminum can stop it. The mass is going to stay the same because you're just trading a proton or a neutron for a proton. And remember, we don't consider electrons to have any type of mass. They do, but it's actually neglectable is what we call it. And then it is going to increase your atomic number because that neutron turns into a proton, meaning you're going to get a new atom. Notice what we're looking here is carbon 14 into nitrogen 14. And so you're getting a carbon breakdown of a carbon isotope that we use for carbon dating. This is a better way of looking at it in that nice little equation thing. You still have your parent nuclei or element and your daughter element or nuclei and your beta particle. Notice it's just that electron, not going to affect the mass. Mass will go straight over, but you're going to increase your atomic number so that it goes up by 1, and that's going to tell you what the new element is. All right, so that's how it breaks down. Last up, we have gamma decay or gamma radiation, and really gamma radiation comes off of both of the other two. It's really just the energy that's released. So notice no mass, no atomic number, no anything except for pure energy, because a photon, which is what gamma waves are nothing more than pure energy in a particle type form that can travel in a wave type pattern. It's very dangerous though. This is the stuff that's coming out that will hurt and kill you. When you get hit with gamma radiation, you don't become the Hulk, you become soup. It's what it changes you into. No charge, no mass, the most energy. It has to be stopped by feet of concrete or inches of lead. That's why it's so hard to get rid of that gamma radiation or to block it and keep it from turning you into soup, which is why atomic bombs and things are so very dangerous, because they release a ton of gamma radiation. If you forgot, here's where those gamma rays are on our electromagnetic spectrum. They're all the way over here on the shortest wavelength, aka the highest energy that we have out of all of this stuff. So X-rays are dangerous. Ultraviolet is enough to kill germs and things, ultraviolet C anyway, but gamma, it can destroy most things, and that's where you find those. Again, notice alpha, paper can stop it. Beta, just electricity. We know how to do shielding with that. But gamma, we need inches of lead or feet of concrete just to slow that amount of energy down so it doesn't turn us into soup. Now, this is just a neat little diagram to show how that decays can actually happen on top of each other. Now, even a natural isotope might have a half-life. Uranium is always somewhat unstable. And we're going to talk more about half-life in the next video, so I'm not going to get into it now. What you need to know is it can go through multiple steps, because sometimes in going through an alpha decay or a beta decay, we know how that's going to change the element and the mass, but it might not be stable. It has to hit one that's stable, that's on the periodic table before it really stops a lot of times. So we can look at this and you can see how it goes through a bunch. This is actually what one of your classwork assignments is going to be. You're going to have to follow a uranium breakdown and look at the different decays it goes down. We'll tell you if it's alpha or beta and how many to go through until you get to a new stable element. And this is just a large visualization, a graphic organizer, if you will, to kind of keep how all of this radioactive decay is related to one another. We have things with our types of decay here. We have our half-life that's over there. Notice that fission and fusion would be part of this because it's how that nuclei is made up and what's going on and the isotopes that are created. And so this is just fun for you to look at, enjoy as you need.